Continuing with matrices, I'm going to talk about a full transformation matrix because so far I've been focused solely on 3x3 matrices, but there's an extra component so that we can evaluate the pose of an object completely, which is a translation or a position. And so when I said that right up and forward have a context when I use the item info, and that context is the position of the object in the world space, that is the last component that I haven't addressed that, or I haven't integrated yet with the matrices, so we can have a full description of an object's pose. So we have right, up, and forward for the object orientation, rotation, scaling, etc. And position, after all of that is solved at the origin, we can then move that away from the origin. So we have the world position taking care of that. Now, most applications, or many applications, use a format, a 4x4 matrix, to solve object transformations. And so here, nested inside the 4x4, we have 3x3, where we have right, up, and forward. And at the bottom, in this case of this layout, there are other matrix layouts where it's sort of transposed. But in this layout of rows, we have the translation or the position here at the bottom. So with this, we have 4 vectors that define the pose of our object. This column here is usually used for OpenGL things, so something that like perspective, viewport perspective and stuff like that, that we don't care about. So let's just disregard this, even though of course this 4x4 mentioning is just, it's just for culture, because we're not going to have any 4x4 data type in here. So these 4 vectors can describe the full pose of an object in the scene. And so instead of using the transform node by Akira Azagi, I'm going to use its transform for node, where right, up, and forward still get in. And then here where it says vec, I'm going to put the position of the pose that I'm trying to address. We also have the invert node that uses those 4 vectors. It's called invert for instead of just invert, and it will basically allow me to invert a matrix. And so before I transform a position by the matrix, maybe I want to transform it by the inverse matrix, and so I can use this node to do that. Now I'm going to look into an example. Let's say I have this basketball court, and I have here 2 players, Adam and Charlie. Adam has the ball, and Adam is like facing this side, and we have the hoop in here. There are some questions that we can ask, and that I think this might be a good example to think about matrices and what they allow us to do. So I have Adam and Charlie having their own matrix. So here we of course are looking at the field from above, so we don't see the up vector, but we have the forward vector and we have the right vector. And here for Charlie, we have the forward and the right as well. And we have what we could say that is the field. The basketball field is the world, and so the origin is here. It's like the center of the field is our scene space, our world space, and that's why I have here I hat and K hat. Now there are questions that I can do, and sometimes we have data that comes in a certain context. And to perform operations based on it, we need to change its context so it makes sense. So for example, I have the position of the ball here in the context of Adam. Now, what if I want to know what's the position of the ball in terms of the court or the world? How can I do that? Well, I have Adam's matrix and I have the position of the ball. And if I draw here, data without context means that I don't care what the data comes in. I just draw the data as it is without worrying, like if I want to draw something that is in the context of Charlie, instead of drawing it like this in here, I'm just going to draw it like this. So without any context. And so in this case, the ball, position of the ball, it's something like this. Right, and we can call this the vector, let's say AB, because it goes from Adam to the ball. And I want to know what's the vector that goes from the origin to the ball. So I want to know the vector OB. So what's the vector OB? It goes from the origin to the ball. Well, to do that, I just need to transform the vector AB by the matrix of Adam. So Adam is a matrix, Charles another matrix. And so to put the ball in the context of the world, I use Adam's matrix. So AB times multiplied by Adam's matrix is going to be equal to the position or the vector OB. And so this is going to look something like this. Let's see if I draw it closely. Okay, something like this. So this is OB, position of the ball relative to the world space, not relative to Atom. But this was the data that I had available, and so I had to transform it to check what's its position relative to the world. Sometimes you cannot control if you get a local position or a world position, and you don't have control of that. You can just change the context of the data by transforming it by some matrix. And so let's look into another example. Now I have the hoop, and let's say that Adam wants to know what's its distance to the hoop and in which direction he should be facing. So he faces the hoop. And so the question is, what's the position of the hoop in the context of Adam? So in the context of the world, I have this position here that goes from the origin to the hoop. So I have origin to the hoop. I have this. What I don't have is this relative position, this position that is relative to Adam's spatial context. So what do I have to do to the position of the hoop so I can say that, okay, this is the data relative to the position of the hoop in Adam's context? Well, here I'm going to transform this position by Adam's matrix, but in this case, the inverse version. And so by transforming this position by Adam's matrix, not only the 3x3, but the position, I'm going to get the vector AH, basically the vector that goes from Adam to the hoop. And so it's going to look something like this, maybe something like this. Yeah, so the data of it is going to look something like this, AH. So what we've seen here in these two examples is that the matrix is a gateway to go from in and out of a context. I had the ball in the context of Adam. So I had Adam's context, spatial context, and to come out of that context, I had to multiply by Adam's matrix to put something in the context of Adam. So in this case, I wanted to put the hoop in the context of Adam. So to go inside that context from the world, I had to multiply by the inverse matrix. So the key is the same. It's always the matrix. But in this case, to come out, I multiply by the matrix. And here I multiply by the inverse. So the relationship between Adam and the world space is the key for it. Now let's see another example. Let's say that I have the ball and Charlie's kind of waiting for the ball. He's like, okay, let's see where the ball goes, because I might want to put it here in the hoop. And so I want to know the position of the ball relative to Charlie, so that Charlie can look at it, can track it. So I have let's start from the beginning. I have AB. That's the data. Let's say that this is the data that I have available, right? And I have Charlie's matrix. So what can I do? Well, I can do what I've done here, where I've transformed the ball position by Adam's matrix. And with this, I get the position of the ball relative to the world. And then I can do what I've done here to the hoop, and that I've put it into the context of Adam. But in this case, it's not the hoop that I'm going to put, it's not the world position of the hoop that I'm going to put in the context of Adam. It's the ball world position that I'm going to put in the context of Charlie. And so in this case, I have the ball world position, and I'm going to multiply it by the inverse matrix of Charlie. So the same way I've put the hoop that was in the world in the context of Adam by multiplying by the inverse matrix of Adam, here I'm going to put the position of the ball that is in the world space in the context of Charlie by multiplying by Charlie's inverse matrix. And this will give me, in this case, CB, the position that goes from Charlie to the ball. And this is going to look something like, let's see, something like this maybe. So the data of it will be something like this, Charlie to the ball. Now, one thing about this particular example is that I went from, let's see what I've done here. I went from Adam to the world space, and then I went from the world space to Charlie space. So Adam to world, world to Charlie, because the world is the place where, we can reference all other things. And so if I want to reference one thing to another space, I have to go through the world. Now, is there a way that I could have a matrix that straight away transforms something that is in the context of Adam right away into the context of Charlie? Well, I can do that. And the way to do that is to multiply the two matrices. So what I can do is, instead of doing a position and multiplying it by a matrix and then multiplying it by another matrix, I can multiply both matrices, can have the matrix of Adam times multiplied by the matrix of Charlie, the inverted one. And this, the result of this, the resulting matrix of this, will allow me that any position that I have in Adam's space can be immediately transformed into the context of Charlie. Right? To do the other way around, I basically would have to invert this this matrix. And well, I can either invert it, right? I can, let's say, I can either have this inverted like so, or I could just basically do another matrix multiplication with the inverse order and the inverse values. So I could do this, or I could do, let's say that I want to go from a position that is in Charlie's space and I want to go into Adam's space. So I want to go the other way around. And so to solve this, I would have to put that is in the context of Charlie into the world. So multiply by the Charlie's matrix, and then multiply by the inverse matrix of Adam. And so this would perform the opposite operation. So this is sort of to explain how things travel between context spaces and how matrices are very useful to do that. We can either multiply positions, specifically just by one matrix alone, or we can combine matrices and then multiply their product, multiply positions by the product of that. And basically, this acts as a key between the two spaces that we are trying to transfer positions from. So this is just quick explanation of concepts. Next, I'm going to go into Lightwave and try to apply some of these. So the first thing that I'm going to do here in layout is to have an object mimic the full pose of another object. So far, all the constraints and context changes that I've been showing, they always have some pitfall. Like I keep telling, well, if you rotate or if you scale the parent, this is not going to work so well, etc. So the idea here is that we can finally come to a point where we have the object full pose evaluated and things work regardless, or at least they are much more solid and don't break whenever we move one object or the other or the parent, etc. Of course, there are constraints for that because, for example, I cannot mimic an object pose on a nodal motion level because the position and rotation and scale that are in the output are relative to the parent. They are not relative to the world. And so if I could set a matrix output here, maybe I could do it, but with position, rotation, and scale, I can't do it. I can't even do a skew matrix with these parameters. So of course, most of these I'll end up doing at a deformation level. I will be doing it with displacement. So let's look into the displacement of this cross here. And so here I have the world spot, and basically this gives me access to the point positions of the mesh, and I'm going to transform those so that they match this cube here. And so we've seen the transform node before, but this is transform 4, which takes, instead of just right up and forward, it also takes the position here, and the vectors that I want to transform, they go last. So here I have the item info that it has this object marked on it. And so I'm going to put right up forward world position, and then I'm going to put the world spot being transformed by all these, and then I'm going to plug this on the subtract. And the subtract, as you probably remember, is because I need to output a delta. So I need to make a delta with my initial point position. And so as you can see now, the cross is constrained to the cube. As I like deform the cube, scale the cube, or even change the parent pose, the full pose of the cube is evaluated, and it's transforming the positions of the cross. Now, issue with this is that I didn't take into account the pose of the cross itself. So if I come here, let's say I move the cross, I rotate it or scale it, or I change also its parent, well, then this is going to, it's going to stop working. So what do I want to have in order for this to keep working? Well, I want to have the cross always at the origin, regardless of what I do to the parent or to itself. I want it to be at the origin so that this thing works. So if the cross is at the origin like it is in here, when I activate this works. So let's basically do transform the cross by the inverse matrix of itself. So here I have an item info with self marked on, and I'm going to copy this transform node, and I'm going to call an invert 4, which is the version that takes into account also the position. And so I'm going to put right, up, forward, and I'm going to connect this to this transform 4 node, and I'm going to plug here the point positions. And so now when I connect this in here, you can see that regardless to what I do to the parent of the cross or the cross itself, it sticks to the origin. Great, so now this means that with the result of this, I can transform it by the cube, and it's always going to be there. So if I put this in here, and if I put this in here, now it's constrained to the cube, even if I change the parent. Here you can see me scale the parent of the cross, or here you can see me rotating, let's see, the cross itself, and you can see that the bounding box keeps rotating, but the vertices stick to the cube. Great, so this is one application for matrices. So here you saw me take the positions out of the context of the object itself and put those positions in the context of another object with the transform 4 node. Now let's look into a way to make this a bit faster, because it's a lot of connections involved. So I've made some compounds that try to address some of this. The most important is this vector so multiplication of a vector by an item matrix. And so it's basically going to do the same thing as you see here, but with fewer connections. So if you want to open up inside, there's an extended item info. And this extended item info is it's a very solid item info. And it takes in the item index and then allows me to use whatever item index I plug in here as my transformation matrix. And as the outputs, I can choose two results. I can choose the result of multiplying the position, the vector, by the matrix of the item, or by multiplying it by the inverse matrix of the item. And so I have the two possibilities here. This option here, only 3 by 3, if I put say any value here, it will trigger that the translation, the world position, will not be taken into account. So basically, I'm just going to have, basically a 3 by 3 transformation. It would be just like if I use this node instead of this one. So the world position will be disregarded. So let's look into applying this instead of going with that. So I just put the item ID in here, and I put the position in here. And now let me take this. To replace the whole thing, I have to do both steps. So this one replaces this one, and now I'm going to replace these two. So I'm going to copy this. I'm going to put the item ID of the object itself in here, and I'm going to plug the position that I want to transform. Okay, so this one feeds this one, so I have to feed this one here, and I want the inverse. So this is doing the inverse operation. So I want to feed the inverse in here, and now when I plug the result on this, you can see that it gives me exactly the same. It gives me exactly the same thing. So with this, instead of having like 7 connections or 9 connections, a lot of connections, I can just have these 4 connections, and it sort of does the same thing. So why not use these instead of going crazy about a lot of connections? Of course, it's good that if you know these, so if you can apply it regardless, because this requires an item info and it requires an item ID, and maybe sometimes you want to do some operation that it's not exactly coming from an item. So it's good that you understand the operations that are inside these compounds. Now, instead of using 2 of these, I can even simplify it further by using one of these compounds that basically multiply 2 matrices together. So the first one multiplies A with A, the second one multiplies the inverse of A with the inverse of B, and the third one multiplies the inverse of A with B, and the last one multiplies A with the inverse of B. So I just did all of these to have some options, but this could be also all simplified, but I didn't want to have many control inputs here, so I just decided to go with explicit implementations. And so let's look into the first one. It's probably the simplest one. And so here I have, instead of 1 item info, I have 2 item infos, and I have their matrices being multiplied using this multi node by Akira Azagi that allows me to multiply 2 3 by 3 matrices. So the position of the first one is transformed by the matrix of the second one, and then the resulting matrix is this multiplication plus the transformation of the first one's position. And so this sort of works like an hierarchy, right? The way I have here is that this will behave like 2 objects, one being the parent and the other being the child. And so in this case, we can say that B is the parent of A, because I have item A being transformed by item B, and the position of item A is being transformed by the matrix of item B. So B is the thing that is evaluated last. So in this case, B is the parent of A in this setup. So this is the resulting matrix, and the resulting matrix is transforming the vector that I have coming in here, and that this basically can replace these two operations. So the first operation I have, it's an inversion. The second one, it's a straight multiplication. So basically what I need is this one here. So multiply the inverse matrix of A by B. And so if let me copy this and put it in here. And so let's see, the first one is this one, and the second one that comes in here is this one. And if I plug in here the vector and plug it in here, you can see that I get the same exact result. So this is a way to be very short about this sort of operations. Of course, this doesn't allow me to do many things in between. This implementation with these two compounds allow me to solve something in between, which is nice, and we're going to look into that. And so this is not just another way to go about it. Now let's look into an issue of context of data. Here I have the world spot for this cross object, and the nodal displacement is set to before world displacement. This means that this node editor will be evaluated after the objects are moved. But sometimes we have some constraints about when we want the nodal displacement to take place. And let's say that I want this nodal displacement to take place before the object is moved. So let's say here I have this matrix S for self, which is the object's own motion. And at the moment, the node editor is being solved after the after the transformation of the object itself is applied to the vertices. So our nodal editor is being solved here. So if I draw this, it makes sense that the first thing that I do is to take out the object, the influence of the object itself. So here I have the self matrix inverted. This is what I've done here by having this item info and transform it by the inverse of the object itself, like I have here in the inverse and here in the item A inverse matrix. And so it makes sense that the first thing that I do here is to transform by the inverse matrix of the object itself, because these two cancel each other out. And then after that, I have my target case. My target is the cube mesh. And then I multiply by the target matrix. And so it becomes that the points are constrained to this target matrix. Now, if I come here and I change the order of this, let's say that I put this set to before local displacement. This means that I'm going to solve this node editor before I solve the movement of the object itself. So this is not going to work so well, because what I'm trying to do here, if I change the node editor evaluation point to before the object is moved, I'm going to do this here, and this is not going to work so well. So what I have to do for this to work properly, just as it worked when it was in here, is to first transform my positions by the target, because the positions are actually going to be at the origin because the object wasn't moved yet. And then after that, I transform by the object itself, but the inverted version, so that these again cancel each other out in sequence. So let's look into that. I have here this not working at the moment. So here I used the matrix is inverted, the second one is straight, and here I'm going to go the other way around. I'm going to have the first one to be straight and the second one to be inverted. And so here I have the round cube, which is my target, and this one is going to go first. And then I have here my self, and this one is going to go last. And if I put this here and if I put this here, you can see that now the constraint works again, just like it worked when the nodal displacement was set to after motion. In this case, yeah, it's a bit what this means. It's set after the object motion is evaluated. Okay, so this sums it up, this part about displacement. Let's look at something else where sometimes it's good to have a change of context. I'm going to disable this. I'm going to reset my object position and its parent. And now I'm going to have the object to target this other object here. And so I'm going to do a nodal motion for the cross. And here I have the round cube matrix item selected for this item info. And we've seen before that with the matrix HPB, I can do something that is very similar to target item. So here, if I come here and I do target item round cube, I get this, right? The forward direction points at the cube. And so I can do do that with the matrix HPB. So do I need to put the position in there and this will work? Well, not exactly, because actually what I want is the world position of the cube. I don't want its position relative to the parent. I want the position relative to the world. So I'm going to put world position in there. And now this works, right? It's as I move this object around, or the parent of it, you can see that my cross targets the cube. Now there's a small problem, is that when I move my cross, or when I move the parent of it, this stops working. So I don't have my cross pointing at the cube anymore. So what can I do to fix that? Well, I know that nodal motion is set in the context of the parent of the object, of the item that it contains it. So for example, for this cross matrix, the parent is this cube parent object. I don't know why it's called, this one is called cube parent and this one is called cross parent. I guess I've made a mistake there. But so the parent of this cross is called cube parent by some accident. And so what I want to do is to put the world position of this item in the same context that the nodal motion is going to be applied. So to do that, what I'm going to do is to put the world position of this item in the context of the parent by transforming it with the inverse matrix. So let's do that, inverse 4. And so I have cube parent, and I'm going to put here right, up, and forward, and the world position. And I'm going to connect this here into the transform 4 node. And now I'm going to put the world position of my target in the same context as my object is. So now the position of the target and the position that I set, or the rotation, etc., that I set on this object, they are in the same context. So let's see if this works. So I'm going to put this in here, and let's see how good. Okay, so now when I move the parent, this sticks, which is nice. But what if I, let's say, move my object? Oh, then stops working. It's not working anymore. And I'm pretty sure if I come here and I put target, this is going to work regardless, right? So how can I have this happen also with my cross within the node editor? Well, I have to make a delta between the position of my item and the position of the target, so that instead of having the position that I'm trying to target be this one, I want it to be this one. And I can do that now. I can do that delta because these two positions, the position of the target and the position of the item, are in the same context, the parent context. So I'm going to do subtract, and I'm going to take out the object itself, the position of the object itself. In this case, it's the local position because it's the position that is relative, that is in the context of the parent. And I'm going to take it out to the position of the target. So now when I move the object itself, it's going to keep targeting the cube. Or if I, let's say, rotate the parent, or I scale the parent, right? It's going to keep tracking this cube. So this might feel a little bit like, why am I wasting time learning how to do something that I can just do by putting a value here, right? Why do that? Well, the thing is, when you start to understand how to reproduce things that you already have access to and that you can check against, it's very nice that you can apply, you can build up these things without requiring explicit objects. You can just do these in abstraction. So it's very good to be able to reproduce things that you take for granted in nodes or in an abstract environment, so you don't require things from the environment, from the 3D scene to be able to do them. Okay, so let's look into another example. This one is maybe a bit more tricky given the orientation. So I have this mesh. Let me maybe reset all of this. I'm going to take out the nodal motion, set object, and maybe put this in here. Okay, so put this to the side. And so I have this mesh here, and you can see that its center, even though the mesh is around here, the center is at the origin. And one thing that is really, really nice about matrices is that allows me to orient the mesh in a way that, it favors whatever calculation I want to do. Let's say that I want to put this mesh into the origin. It's the mesh is out here, but I want to look at it or to make some calculations in it, but if it was resting at the origin, not outside, not away and oblique like it is. So I can do that with matrices. And let me come here to the displacement node editor. And so I have two things in here. I have two objects, one called root and the other one called deformer. And we're going to look why we have those two after. At the moment, what I'm going to do is I'm going to use the root object to reproject or make a projection or pose my mesh from its current location into the origin. So I'm going to multiply this by the inverse matrix of the root. And so before we know that we have the object itself being moved, rotated, scaled, and I inverted that. But here I'm going to use another object to define that pose, not the object itself. And so for that, I'm going to use the root object. And so let's do that and have here the item info for the form root. And so I'm going to put the item ID in here, and I'm going to pass the world spot in here, and I'm going to put the result onto the delta. Okay, so at the moment, this is it's a bit crazy. It goes out there. Let's see if I can pose this better. So let me see the root. It should be the inverse. I don't want the result. I want the inverse. But let me try to put the root closer to the mesh. So it's sometimes a little bit hard to do here in Lightwave, but let's see if I can do this just well enough. Okay, so I think it's on the surface. Now I just need to rotate it, and I'm going to roll it a little bit so it aligns a little bit better. Okay. So I would say that this is sort of on the surface of this object, right? And so now I want to use the pose that this root object has to place place this mesh at the origin. And so we can see that by plugging this in here. And you can see that now my mesh, of course, it's not perfect because I didn't align the root perfectly with the mesh. It's a bit hard here in Lightwave, but you can see that now the mesh went to the origin like it was, like I was taking out the pose that it had. And I can, let's say if I change the coordinate system to a local, I can now move this up and down. You can see that I can have the origin, the root, to become sort of the origin for the point positions, and I can change that interactively. Maybe let's say I want to better alignment here. And so yeah, this seems to be a better alignment. So this allows me to project this mesh into a sort of a pose that maybe it favors some calculations. So maybe now I can make some decisions based on the mesh position along the Z axis that before that wouldn't make a lot of sense, because I wanted something that was along this direction, not along the world Z axis, for example. So this is a way to basically create projections of things and pose them in a favorable way. Now I have in this root, I have a child item called deformer. So if I put the positions in the context of the root, and then I multiply it by the pose of the deformer, what do you think it will happen? Well, since they are overlapping, the root and the deformer are the same. The object is going to go back to where it was. So let's check that. Here I have the deformer, and I'm going to put this item ID in here, and I'm going to put the result at end. Right, so now what's going to happen? Well, actually, it seems that it rotated a little bit. Let me check this out. Yeah, it has some rotation about it. Let's see if the deformer has some rotation. Yeah, the deformer had some rotation. So let me reset that. Okay, so since both the world pose of both the root and the deformer at the moment are the same, I activated the displacement node editor again. You can see that nothing is happening to the mesh. So the first multiplication put the mesh at the origin, and the second one put the mesh back where it was. Now the cool thing is that I can place the root at a specific place. Let's say I want to place it here, but then I can transform the deformer, and what's going to happen is that it's going to use that root position as, let's say, the rest pose. When we have bones here in Lightwave, there's a thing called a rest pose, or any deformer setup. There's a rest pose, a rest matrix, and then there's a deformer that makes something be different from that rest position. And so that's what we're seeing here. The deformer, when it's reset, it has the same pose than my root, but as I start to manipulate the deformer, it's going to have a pose that is a little bit different, and that is going to be felt when I put it back. So I can, let's say, come here to the root and place it in here, and now this will be the center of my rotation. And I can scale from that position. I can pick up the root again, and let's say I'm going to put it here in this corner. And now that corner will be the center of rotation and the center of scaling, etc. And let me just do something in between these two. Just going to put this, let's say, here. And I'm going to put this somewhat around here and maybe a little bit in. And let's say that I want the deformer to affect just the positions that are positive on the z-axis. So if I put this in here, you can see that at the origin, these positions are positive on the z-axis and these positions are negative on the z-axis. Let's say that I want to have a small gradient. Let's see. Oh, I can just do a max. Let me just do a max. So split vector. And so this allows me to evaluate the positions as they are here at the origin. And so I'm going to do a max, or no, I'm going to do a logic node, scalar logic. And if position is greater than 0, then output 1, otherwise output 0. Okay, and I can even do maybe I'm going to do a remap. So there's a soft transition. I think that might be a little bit better. So Z position, and from 0 to point 2, I want a mixer to be fed with a gradient that goes from 0 to 1. So I'm going to have a mixer in here. And this mixer is going to take in the opacity this gradient that I'm doing with the remap. And so for when this is 1, I want it to be deformed. When it's not 1, I want it to be as it was. So if I plug this in here now, you can see that when I come to the deformer and I rotate it, for example, only the part that is in front of the root Z axis is going to be deformed. I can of course change the parameter here. I can say 0 to 1. So that's going to make a bit of a too soft transition. Maybe it's not very pretty. So 0.2 seems to be, or let's say 0.4 seems to be sort of fair. And I can move, as I move the root, for example, I change that Z position, right? Because the root is transforming the positions here before that evaluation. So when I come here and let's say that I move the root up and down, you can see that the gradient also changes. And so I have this change happening. So this is the fundamentals of creating a root and a deformer. You have the deformer being a child of the root. The root is posable, so you can pose it anywhere you want. And then the deformer is a bit different when you manipulate it. It has a little bit of a difference from the root, and you can see the difference between both. So the root places the mesh at the origin into a pose that we kind of like. So we center it and we scale it the way we want. And the deformer then gives it the pose that we want, that is a little bit different, that is an offset from the root. So I know this is a bit, maybe it's probably a lot to absorb, but let me tell you that sometimes even I make a lot of mistakes in terms of space context and what do I have to transform? Do I transform something by the matrix or the inverse matrix? And well, what I've tried to give you in here was basically an overall view of context, of the idea of context, the idea of order of operations, and what you have to do so that the data that you work with is in the same context and you don't have mismatches between what you were expecting to do and what you can, what you're actually doing. That's why sometimes it's nice to try to grasp what the data looks like. What's the data without the context of the things that I'm seeing in the 3D scene. But definitely this comes better with time, because it's at times you're just not grasping what's the context of the data that you're getting, or that you need to transform something before or after. And so for that matter, I'm just here gonna finish this part by showing that I can do this as well when I move the object. So at the moment, I'm at before local displacement. So this means that when I move this object, this is gonna fail, right? So what do I need to do to make this work? So regardless of if I move the object or not, in order for this to work, well, I need to basically do something similar that I've done before. And so since the world spot comes after the context of the data that I'm getting is before the object is transformed, but I still want to access the point positions when the object is transformed, I'm going to do it myself. I'm going to multiply the point positions of the object by its own matrix. And so I'm going to put here, just the item ID. I'm going to put this in here, and I'm going to deactivate this for now. And so this at this moment, I'm going to transform the point positions of the object by its own matrix. And so I'm going to replace here some inputs. So this was going to the mixer. Instead, this goes to the mixer. And then at the exit, after after I do the calculations that I wanted, that match what I was doing before, I need to put the object back into without its transformation. So here I transformed it so I could evaluate the world position. But after I've done that, I need to put back into the context that the object is, which is before it is actually transformed by its own motion channels. So I'm going to come here and I'm going to put the item ID in here. And now instead of using the result, I'm going to use the inverse. And so basically what I've done with this and with this, it's a bit of a conjugation if you are reminded of the term. So here's my main operation, and my main operation was having this root and the former setup, but before and afterwards I change the context of my vectors so I can have them happen in a specific context. And so here I took the positions out of context, I transformed them, I did what I wanted, and then I transformed them back to the previous context. And so this is what these two compounds are doing in a way. So now when I plug this in here, you can see it works exactly the same. And the only difference is that when I move my object, it still works. And before, if I would do this, like I can, let's say, move this object like so, do it like this, let's see, like so, and then I can move. Now I'm going to change the root. Let's say I'm going to reset these two, rotation of both, and I'm going to change the root, and I'm going to realign it with my object. Let's see if I have. It's a bit harder here in Lightwave to do these sort of things. Let's see. Okay, so let's see if I can align this again in a good fashion. Right, now I need to rotate it. This is on the surface. Let me rotate this. I want forward direction to go along the surface, something like this. And now I want to roll it a little bit. Okay, let me just put this in local. That's already local. Okay, yeah, so this is fine. Let me plug this back again. And now when I change the former, you see that it still works. Now, if I wanted to have this, let's say, in before world displacement, I don't need to do this mumbo jumbo because instead of happening here, it's happening here. So the object was already transformed, and the world spot is already taking in consideration the final position of the vertices of my mesh. So if I wanted to do this after the motion channels, I can, let me just copy this, and I can just disregard these two steps, right? I can just come here, this step and this step, I don't need them. I just need to replace the connections that this one hold it. So this goes in here and this goes in here. And now I can get rid of both of these. And let me put the output here. And if I put this here, of course, now it doesn't work. But if I change to before world displacement, you can see that now it works. If, let's see, funny, it's not working as I expected. Let's see, fruit, the former, inverse. Oh yeah, I forgot the delta. Oops, I need the delta. If there's no delta, this doesn't work as expected. Like I said, context, context, context. That's why sometimes a bit of a pain to work with position vectors, because you forget about something and then things just stop working. And so, yeah, like I said, you can have it in the before world displacement. So after the motion of the object itself has been evaluated, and it's going to work as this one was working before the object pose was evaluated. So this is it. I'm sorry if it's too much to absorb. This is very important to understand these concepts, to be able to have data flow from one spatial context to another spatial context. And I'm going to reuse this again in the next topic about normalization, to create fall-offs, to create basically areas of effect for the deformers. So it's not, it's a bit like I've done here with the remap node, but for things like the length of the distance of the points, etc. Cheers.